Okay, hi everyone. So orthonormal bases. When are vectors orthonormal, and what's an orthonormal basis? So vectors are orthonormal, like e1, e2, e3 are orthonormal if e1, e2 is 0, e1, if they're all orthogonal, and normal means normalized to be unit length. So e1 should be 1, e2 should be 1, e3 should be 1. Okay, so you could think of like I hat, j hat, k hat in three-dimensional space. They're all at 90 degrees. Clearly, they're going to be independent, and they all have length 1. Okay, so orthonormal means length 1 and orthogonal. Okay, and an orthonormal basis is just a list of orthonormal vectors that are a basis. Okay, but orthonormal are going to be automatically independent, but they should also span the whole space if they're an orthonormal basis. Sometimes called an ONB because it so often comes up. An orthonormal basis is an ONB. And they're often called E1, E2, E3, E4, etc. Okay. Prove every orthonormal list is independent. So let's suppose that the E1, E2, E3 are an orthonormal list, and say that we have a dependence. I need to show that all the coefficients are 0. Well, just take the dot product of both sides of this with, let's say with E1. If I take the dot product of this side with E1, by linearity, so I'm going to take this whole thing and dot product with E1, by linearity in the first slot, I'm going to get, when E1 hits E1, I'm going to get 1. And then when E1 hits E2, I get 0. And E1 hits E3, I get 0. And so I will get A1 times 1. But if I do it with the right side, I get 0 E1, which is 0. And that shows that A1 is 0. Similarly, by taking the dot product with E2 on each side, we would get that the coefficient A2 has to be 0, etc., etc. Okay, that's one way to do it. I think the book does it a slightly different way. Give a simple formula for the norm of a Lin-comb of orthonormal vectors, which does not hold for a linear combination of non-orthonormal vectors. Okay, so let's imagine we have a A1, E1 plus A2, E2 plus A3, E3. This is a linear combination of the orthonormal vectors E1, E2, E3. We're not saying this to 0, we're not proving independence, we're just, here's some linear combination. What's the norm of this vector? Let's call it V. What's the norm of V? Well, if we take V dot V, we can calculate V squared and then take the square root. So what's V dot V? It's V dot itself. And what you're going to do is all the cross terms are going to be 0, right? By linearity, we can do this dot this, which will be A1 bar. So this one it has to pull out with a bar. This one has to pull out without a bar. And we get E1 dot E1, which is 1. Okay. And then, E1 dot E2 will be 0, dot E3 will be 0. So now we're on E2 dot E1, which is 0, E2 dot E2, which will give us now, E2 dot E2 is 1, so we're going to get an A2 and an A2 bar when this one pulls out with a bar. And then that 1, we will just not write. And then, similarly, we're going to get A3 bar. Okay, so that means that the norm of V squared is just you sum the norms of the complex number coefficients. Or real number coefficients, then you don't need these bars or anything. So that's the formula, and we proved that it works just by computing this. Okay, let's look at number 4. So if the V's are a basis, any vector can be written as a Lin combination of them. If they're an orthonormal basis, what's a formula for the jth coefficient, right? What's A2? So the key here is that typically to write some vector as a linear combination of a basis, we have to solve a whole linear system, an n by n linear system of equations. And that's pretty annoying to do. A computer will do it for us, but we often want to do it analytically and then take the result and keep computing with it to discover things. And so it's useful to have a formula like, what's A2? Well, we know, let's say we're given the vector v, and we know it can be written like this, but we don't know the a's. So all we know is the v. What we should do is just take v dot product with our second basis vector. Because if you do that, you can imagine replacing the v with all of this, and then the v2 hits v1 and gives 0. The v2 is going to hit everything and give 0 on everything, except when it hits this one, in which case we will get that this is A2, V2, V2. The A2 will pull out, and we get V2, V2, which is 1 if the v's are an orthonormal basis. In other words, the second coefficient is just this. Okay, what's the jth coefficient? Well, it's just the vector dot product vj. So if you're given a vector v and you're given an orthonormal basis, you can immediately compute the coefficients by just computing a dot product. You just compute one dot product and you've got the coefficient immediately. So you don't have to solve a linear system of equations, which is very nice. Okay. And notice I had to take the v2 on this side because I wanted the a2 to pull out nicely. If we do it the other way, then we're going to get the conjugate. In other words, aj bar is going to be vj dotted with v. Because if we take the conjugate of both sides of this equation, that's what we get. Okay. All right, this one is exercise 4, and I want you to actually do this one yourself. But just to talk about it briefly. So if we take a vector space of continuous functions with an inner product given by instead of summing the squares, we just multiply these things together and integrate instead of summing. Then these are an O and B. So if you integrate, for example, cos of 2t times cos of 3t dt, you are going to, over negative pi to pi, you are going to get 1. Well, you're not going to get 1. You're going to get pi, I believe. And so if you divide both of these by square root of pi, then you're going to get 1. Okay? So this is going to be 0. This is going to be 0 because I took different ones. These are going to be 0. But if you change this to a 2, now you would get a pi. And then when you divide, you'll get 1. So I really messed this one up. But the point is that these vectors are orthogonal. They're at 90 degrees in the infinite dimensional space of trig functions or continuous functions. These vectors are sitting at 90 degree angles. And they're unit vectors. They each have length 1. Because if you dot it with itself, you're going to get 1. If you dot cos 2t with itself, you're going to get 1, provided you've normalized them there. So if you have some function like the tides, you've been tracking the tides near a certain beach, f of t is the height of the water at a certain location as a function of time, and you want to know what's its coefficient of maybe sine 2t over square root of pi, well, we apply the previous formula. We can just immediately write down the coefficient. It's a dot product. So the coefficient of sine of 2t over root pi of that orthonormal basis vector is just you multiply by f of t and integrate dt negative pi to pi. Okay, and then out pops the coefficient that you would use to represent this as a linear combination of cosines and sines. And you really need to watch this video. It is one of the best videos about math on the internet. And so you just gotta watch it, please. It's wonderful. And maybe I'll put something on the quiz about it so that you watch it. Okay, let's look at this one. say the E1, E2, etc. are an orthonormal basis, prove that V is equal to this. Well, that's what we just proved, right? Any vector V can be written as a linear combination of a basis, but if the E sub i's are orthonormal, we know how to compute A sub I. A sub I is just take that V and dot it with E sub I. And so that's why we put V dot E1 as the coefficient of E1. That's why we put V dot En as the coefficient of En. Because those are the formulas for the coefficients that we just proved. And previously we also proved this. We proved that the norm squared of a vector in an OMB is just the sum of the squares of the coefficients. We proved that on the previous page. And now we know that the coefficients are just these dot products. So, boom. That one's done too. This is just basically collecting results we already proved. And now let's look at this one. U dot V is this. Well, this will just come from expanding U. So U dot V will be, well, let's expand U as a sum in the E sub i's. Well, what's the coefficient? Well, it's take the dot product of U with E sub I. Then comma, let's expand V the same way. Let's say sum over J, sum over I. Now we're going to take V and compute its jth coefficient and put that in front of EJ. And that's how we don't even have to solve a linear system of equations to find these coefficients anymore. All those problems from chapter 3 are much easier now if we have an orthonormal basis and an inner product. And so then, what's happening here is we're linear in this slot, we're additive and conjugate linear in the second slot. And so that's why you get these bars coming out here and no bar right there. And all the cross terms, E1, E2 is 0, E1, E3 is 0. The only terms that survive are the E1, E1, which then gets its coefficient next to a 1, which is E1 dot E1. And you just keep doing that. E2 will come out with a 1, and it'll keep its coefficient. And finally, En was a 1 that we don't write. And this pulled out from the first factor, and this pulled out with a conjugate bar from the second factor. Okay, definitely watch this movie too. This is a great movie, and this is a great scene. So in this scene, they're talking about having like satellites flying around Earth, right? So they're flying around, and you could try to choose like some sort of Cartesian system on Earth to describe the flight of this satellite or this rocket ship going to the moon or whatever. But much better is to actually just use, like, imagine you are sitting on the rocket ship. You have your velocity vector, then you have your acceleration vector, which you know by gravity, and here I drew it so that it's sort of, let's imagine we're flying to the moon. Okay, so you know your velocity vector, and then your acceleration vector might look like that. And so what you do is you say, okay, let me choose an orthonormal basis called, I'll take my velocity vector and I'll call it capital T for tangent. And it's going to be TNB. And then I'll take my acceleration vector and I'll sort of project away the component that's along the tangent. And then I'll normalize to be length 1. So that'll be my TN. And then I'll take the cross product of these two to get a third vector that I'll call TNB. And so now this is your three-dimensional coordinate system. You're just going to write the coordinates of everything around you, including the moon and the Earth, as linear combinations of this new frame of reference, this new basis, the TNB frame. You call it T is E1, N is E2, and B is E3. Now, the key here is how did we produce N? We knew the velocity and we knew the acceleration, and they aren't going to be at 90 degrees, depending on how we're moving. So what we do is, and let's call the velocity V1 and let's call the acceleration V2, and we'll just choose a random third vector V3. That's our basis, okay? So what we're going to do is, first, we're going to produce E1 by taking V1 and dividing by its length. That just normalizes it so that it has length 1, okay? Now what's going to be our E2? Our E2 is going to be, well, we're going to take V2, which points over there, and we're going to subtract away this piece that we don't want. What is that piece? That piece that we're going to subtract away is the projection onto the first vector. So we're going to subtract away the projection of V2 onto V1. So V2, V1 over V1, V1, V1. Okay. This is Graham-Schmidt. This is just the projection formula from earlier. Okay. Now, hold on a second. I'm a little bit worried, though, because of this V2, V1 or V1, V2. Because if we're in a complex space, we're not in a complex space here. We're in a real space. But if we were in a complex space, we want the formula to be correct. So let me just remind you, how do you project? If I project onto a vector V, and I project the vector U onto it, that means I should draw the shadow, and I'm trying to find this vector P, which is some scalar multiple of V. And what do I know about P? It should be 90 degrees. So that means that this vector, U minus P, is orthogonal to V. So U minus P should be orthogonal to V. So that's this equation. And now I will solve for C. Let me just make sure, yeah, so if I put this here, I'm good. If I put it over here, I might be wrong. So let's do this carefully. U minus CV, V equals 0. UV minus CVV equals 0. And now because I'm linear in the first slot, is our convention, I'm going to pull out the C without a bar. Good. I think this is, I happened to do it the right way, but let's see. V, and that means that C is UV over VV. Okay, and so the key here is that the vector we're projecting onto should appear in this right slot up top, and the vector we are projecting from should appear in the left. So let's see if that was, did I do that right? Yeah, I want to get rid of V2 and project it onto V1, so my V2 goes there. Good. Now what I'll do is I'll take whatever that vector is and just divide it by its length. This is pretty annoying to write, but in practice you just compute the norm of this vector, whatever it is, and this will make this new vector E2 to be unit length. It'll just have unit length. The key idea here is to make sure you understand why we're subtracting this piece. We've got our V2, it's pointing in the wrong direction. We want to get rid of this piece so that it's now this way. And then this division right here that I'm going to circle in blue shrinks it down to be unit length. Okay, so that's the idea, and this is the process. This is how we do it. Now, the nice thing is, if instead of V1, if we used E1 here, then we could do the whole thing, but just with E1, 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 but this is a 1, and then E1, 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 but this is a 1. So then the formula looks a little simpler. If we use the already normalized vector, our denominator is not needed, okay? But we don't have to use the normalized vector. We could use the original vectors. And then how do we produce E3? So this is the process. You take E3, or no, you're going to produce E3, and you produce it from the third original vector. But you're going to subtract off the piece that's along the second vector. I'm getting a little, and then you're going to subtract off the piece that's along the first vector. No, I think I want to subtract out. Let's start using the e's. So let's subtract off V3 on E2, and subtract off V3 projected onto E1. So now I don't need the denominator because I've already normalized my e's, so I'm not even going to write that. And this formula is definitely correct. So I take my V3, it's pointing in the wrong direction. I subtract off the piece that's pointing along the E2 direction, and I subtract off the piece pointing along the E1 direction, and that makes it so that E3 is orthogonal. This new E3 produced that way is orthogonal to E2 and orthogonal to E1. And let's see that. If I take this vector here, what is E3 dot E2? I should get 0. And what you'll see is going to happen is if I dot this thing with E2, I get a V3 dot E2, and then a 1, and a minus V3 dot E2, and then a 0, because the E2 hits the E1 is 0, E2 hits the E2 and is 1. Then I've got this minus V3 E2, then E2 hits the V3, it gives me a plus V3 V2, so I get, I get minus plus the same thing, which is 0. So you can check, that's the Gram-Schmidt procedure. Let me just do it one more time. So you have some V1 and you have some V2, and those don't look very good. So what you do is you project V2 onto V1 and you subtract that piece off, so that gives you a new vector, and then you normalize that vector so that it has length 1, and you should also normalize your original vector so it has length 1. And these two little vectors are your orthonormal basis. Okay, and in formulas, that means you produce E1 by just dividing V1 by its length to make it a length 1 vector. And you produce E2 by taking V2 and subtracting off its projection onto E1, which now, because I'm using E1, it's already normalized. This is a 1, and I don't need it. And if you have more vectors, you just take the bad vector that wasn't pointing in the right direction, and you subtract off its projection along E2, and you subtract off its projection along E1, all the previous ones, and that's how it goes. Now notice, here we are working within the span of V1, we just rescaled. Here we are working within the span of V1, V2, and we rescaled to get E1, E2. Then we went to the span of V1, V2, V3, and we worked to get E1, E2, E3. So each time you sort of work up one at a time, increasing in size the subspace that you're moving along. Okay. So in other words, when I was producing E2, I didn't need to worry about V3 at all. Right? I'm just working in the V1, V2 span. Okay. Apply Gram-Schmidt to this thing. So this is done in the book in detail. You should really understand this to make sure you understand Gram-Schmidt. Whatever I just said, you're going to now do it with specific formulas in a vector space of polynomials. So really do that one, and the book has it in full detail. Prove every orthonormal list extends to an orthonormal basis. So if you have an orthonormal list, E1, E2, E3, but maybe your vector space is actually 7-dimensional, well, these are independent, so any independent list can be extended to a basis. So just do that. Just extend it until you get a basis for the whole space. And now just apply Gram-Schmidt. You see, you're good on these three. So then you take V4 and you just start subtracting off. So you produce E4 by taking V4 and subtracting off the piece of it that's along E3 and subtracting off the piece of it that's along E2. And so you're just working within this 4-dimensional space until you've got another, that should be E1, another vector. And then you go and do the same thing to V5 by subtracting off its projections onto the E1 through E4, etc. So that's the end of the proof. So you just extend to a basis and then apply Gram-Schmidt. That gives you an orthonormal basis. Okay. Let's read this one. Read it and maybe pause the video to think. So remember, we proved that T has an upper triangular matrix exactly when the min poly of T factors into linear factors. Okay, that works over R and over C. Over C, every min poly factors into linear factors. So over C, every operator was upper triangularizable. But over R, not every operator will be upper triangularizable, but if it's min poly factors into linear factors, you're good. Now the key here is we didn't require distinct linear factors. If you're so lucky that the min poly factors into distinct linear factors, then not only are you upper triangularizable, but you're diagonalizable. Okay. But here, give a condition that T has an upper triangular matrix in some orthonormal basis. it's actually going to be the min poly factors into linear factors again. Because of the whole idea that you should see now from Gram-Schmidt is we're just sort of going onward, up and up and up, taking into account more and more vectors as we go. And so you're just working in these spans. But that's exactly what an upper triangular matrix does. Remember, a matrix is upper triangularizable exactly when there's a basis, v1, v2, v3, v4, etc., such that T maps v1 into v1. T maps the span of v1, v2 into the span of v1, v2. In other words, the span of v1 through vk is invariant for every k. Right? You remember that from chapter 5? The span of v1 up to vk, even if you eventually go up to vn, for every k is 1, 2, 3, up to n, the span of vk should be invariant under T. But so then choose that basis and just apply Gram-Schmidt. Gram-Schmidt also works and just rescales this one, then takes v2 and subtracts some amount of v1, then takes v3 and subtracts some amount of v1 and e2, then takes v4 and subtracts some amount of e1, e2, e3. And so it works within those invariant subspaces, and so you can just apply Gram-Schmidt and you don't mess up the upper triangularizability of your basis. So then you take your basis that you know exists for the upper triangular matrix, and you apply Gram-Schmidt to it, and now you have a new basis, E1, E2, ... all the way up to En, which is orthonormal, and didn't destroy the upper triangularizability. The matrix might look different now. You've got different vectors, different basis, but you were working within these invariant subspaces the whole time. Okay. All right, you should know this one. Quiz yourself on it. A linear functional is just an operator. No, sorry, it's not an operator. It's a linear map from V to F. Okay, these are special. Remember in chapter 3, we looked at linear maps from V to W. And then in chapter 5, we looked at linear maps from V to V. So we took the special case where W equals V. And now, if we take the special case where W equals F, the field, a one-dimensional space, the scalars, that is called a linear functional, or the dual space. And I guess your book says it calls these things phi. It's like a phi, Greek word, Greek letter. So phi takes a vector in our vector space and spits out a scalar. So phi of v is a scalar in F. And the dual space, v dual or v prime, is just by definition that space, the space of all linear functionals. All the linear maps that take vectors in V and spit out scalars. Okay. An example of a linear functional on this space, which is spanned by 1, x squared, and x to the third, would be to integrate from 0 to 5. So that you take p of x, you take some polynomial in that space, and you send it to the integral of p of x with, I don't know, anything you want, x. Okay, that would be fine. Or you could even replace x by the cosine of 2x. Okay? Even though cosine of 2x is not in this space, it's just going to play a role as something to integrate against. This will still be a linear map. It's linear in the variable p. Because if you replace p with p plus q, you're going to take the integral of p plus q times the cosine of 2x, or whatever you put in here, like to integrate against. And by things we know about integrals are linear, so we can do p times cos 2x dx first, and then add it to what we get when we integrate q against cos 2x dx. Okay, so by linearity of the integral sign, we get linearity of this thing. Okay, and now this is the fun thing here, is that even though this is not in our space of polynomials, if we integrate against this space, there's always some polynomial who we could have integrated against instead of the cosine. So the picture I like to think about this is, let's say we're in some subspace of nice functions, like polynomial functions, and we're in here, okay? And then we could, if we want, step outside of our space to some bigger functional space and find like a cosine pi t instead. And down here are all the 1t, maybe they're just polynomials in t, whatever. Some smaller dimensional space down here. And what we're going to find is that integrating against cos is actually the same as integrating against the projection of cos down to our subspace, the orthogonal projection, which we're going to learn about in the next section. And so this is the q of x that exists. And then if you take any other vector, this vector, or that vector, or this vector, or that vector, and if you integrated it against cos, you're just going to get the result of integrating it against q, because the integral just cares about what's happening inside here, and this 90-degree part won't matter. Okay, that's the picture I like to think. But the precise statement is the Riesz representation theorem for finite dimensional. So there's an infinite dimensional version of this, but it's more complicated. You have to do the convergence of infinite series in the infinite dimensional spaces. But, so what does it say? It says, given any linear functional, any linear map from V to F, right, sending a vector V to some number phi of V. If V is an inner product space, meaning if we have some inner product defined on it, right, inner product space, then this linear functional, whatever every linear functional, is secretly just the dot product of V against some vector q. Okay, so then there exists some q in the original space, in the inner product space, such that secretly doing the linear map phi of V was really just dotting V with q. Okay, and I put the q over here because our book this map should be linear in V, and we've decided that we're going to have linearity in the first slot and conjugate linearity in the second slot. So really this is like the bra in quantum mechanics, if that makes any sense to you. But that's the idea. So there's always some vector that every linear functional, no matter what it is secretly an inner product, right? So if the inner product is an integral, then we're really doing the integral of whatever. That doesn't really, yeah. Okay, so, we're supposed to prove it. Okay, well, then that means I need to produce this q. So what can I do to produce q? Well, okay, so choose an orthonormal basis. That's the key. Now q won't depend on my choice of orthonormal basis. There's many different orthonormal bases for any space, but just choose one of them, and I'm going to figure out what q is. I'm going to produce q. I know how to do phi of V, and I know that V is equal to some coefficients in the EI, but I actually know those coefficients. Those coefficients are what I get when I do V dot product with EI on EI. Okay? So phi of V is just phi of this thing. But phi is linear, right? Phi is a linear map. So I can do the sum over I of V EI. Phi applied to EI. So now this is a number. And this is a number now, right? Because phi is a linear map. It takes vectors to numbers. So this is a number. I can pull it inside here. Okay, but if I pull it inside there, I'm conjugate linear in the second slot. So I have to do a phi EI bar EI. And that's the sum over I. But I'm additive in this slot, so I can pull the sum inside. So I've got V, and now I've got a sum of the phi EI bars EI. And this is my vector q. Okay? So there you go. I've shown that q exists, and in fact q is exactly this thing. I've been given the phi, so I can calculate phi on my orthonormal basis, take its conjugate, and I can linearly combine the orthonormal basis, and I get a vector. And I've shown that phi of v is just a dot product. Okay, bye, Henry. See ya.